My name is Iyad Obeid, Director of the Neural Instrumentation Laboratory at Temple University. In this short video, I will be summarizing my presentation from the 2010 IEEE EMBC conference in Buenos Aires. The co-author of this work is my graduate student, Karthikeyan Balasubramanian. One of the key interests of my lab is the design of brain-machine interface instrumentation, with a focus on implantable and wireless devices. Specifically, we were interested in optimizing the BMI signal processing pathway for implantable systems in which processing power will be severely restricted. In contrast to research-grade BMI systems in which electrical and computational power are essentially limitless, implantable systems will need to be designed to make optimal use of a relatively limited electrical apparatus. Historically, BMI instrumentation has been designed in an ad hoc manner, meaning that engineers have effectively had to guess at how to combine a large number of potential signal processing blocks. This strategy has been successful, but it is dependent on access to powerful computing platforms. In contrast, the long-standing goal of developing fully implantable BMI instrumentation will require designs that are specifically optimized for a low-power, computationally limited environment. It will not be sufficient to simply use existing signal processing strategies that were not developed with computational efficiency in mind. Specifically, we are interested in determining what is the optimal allocation of resources in a limited hardware environment. For example, do we achieve superior neuroprosthetic control using a highly accurate spike sorter that requires so many resources that we are limited to, say, 20 channels per chip, or with a moderately accurate spike sorter with a smaller footprint that would allow up to 50 channels per chip? Furthermore, can neural plasticity be leveraged to overcome limitations in the signal processing pathway? For example, in a closed-loop BMI environment, can the brain adapt itself to overcome the information that is lost by a spike sorter that is only moderately accurate? To answer these questions, we are developing a simulation platform that will model the entire closed-loop brain-machine interface signal processing pathway. The platform is comprised of three main elements. 1. An adaptive computational model of motor-controlled neural tissue, such as the cerebellum. 2. A testbed brain-machine interface hardware platform. And 3. A realistic prosthetic limb model for the virtual brain tissue to control. Multimodal feedback from the prosthetic limb back to the neural tissue closes the loop and drives neuroplasticity. In the remainder of this presentation, we will focus on the second element of this simulator, the reconfigurable hardware architecture for BMI instrumentation. For the purposes of rapidly evaluating BMI instrumentation for implantable hardware applications, we propose the use of the Field Programmable Gate Array, or FPGA, which is a reconfigurable hardware tool that has already been demonstrated in several neural signal processing applications. One key advantage of developing for the FPGA is that the hardware description language code that is generated to program the FPGA can be directly translated into ASIC designs that can then be optimized for size and power and packaged into neurochips. Specifically, we have developed and implemented a new embedded system architecture for neural signal processing. At the core is a central processor, such as the soft-core microblaze we used, that coordinates data processing between any number of user-defined processing elements, or P-cores. Instead of data passing directly from one P-core to another, it is shuttled through a local bus that is managed by the processor. In our implementation, we used a spike sorter of our own design based on fuzzy logic rules that are trivial to implement in hardware and that do not require any user training. This architecture is scalable, easily reconfigurable, and will lend itself to real-time operability in which precise upper limits on P-core processing times can be defined. Our neural signal processing platform required roughly one-third of the resources of a Xilinx Vertex 5 FPGA, with spike detection and sorting performance that was identical to a MATLAB benchmark simulation. Since neural signals are sampled at a significantly lower rate than the clock frequency of the microblaze processor that we are using, time division multiplexing can significantly improve the system throughput. In our case, we estimate that each processing pathway should be able to manage 100 channels. Since each pathway only used one-third of the Vertex 5 resources, we will be able to fit 3 parallel pathways that will collectively be capable of managing 300 channels per chip. Using our architecture, it will be possible to rapidly evaluate various BMI processing strategies within the context of closed-loop BMI prosthesis control. Importantly, it will allow us to gain insight into the true value of a given signal processing block given its cost as measured by power consumption or use of processing power. It will also elucidate how neural plasticity might be exploited to reduce the size or power of an implantable neural processor. This work has been sponsored by the National Science Foundation, For more information, please contact the Neural Instrumentation Lab at iobeid@temple.edu. Thank you.